You push a heavy wooden box. A ship parts the water. A metal spring snaps back. We navigate the physical world by feel, and our brains are incredibly good at predicting how these everyday objects behave. But a structural engineer cannot determine the stability of a skyscraper based on how heavy a steel beam feels in their hands. When human lives depend on absolute precision, like calculating the maximum load limit of a suspension bridge or the exact stopping distance of a train, gut intuition is no longer a valid metric. To calculate motion safely, we strip away the messy reality of wood, steel, and water to uncover the mathematical rules governing the system. In mechanics, we call these contact forces. They are the specific constraints dictating how objects interact the moment they touch. Mastering mechanics means abandoning the physical sensation of a push or a pull and learning to identify the precise mathematical vectors operating in the background. The most basic of these is the normal force. It is the upward resistance a surface provides to prevent an object from falling through it. If the surface tilts into an incline, the normal vector shifts immediately to remain exactly 90 degrees to that surface. Once a surface is defined, we must account for pulling forces. In mechanics, any force transmitted through a string, rope, or chain is called tension. Looking at this pulley system, tension acts as a constant restoring force. Assuming a light, inextensible string, these T vectors always point away from the connected masses, pulling uniformly throughout the entire length of the rope. Normal force and tension act as the scaffolding of any mechanical problem. They set the rigid boundaries of the system, keeping objects from passing through floors, setting the stage for complex interactions. The most dynamic interaction on that stage is friction. Before an object even starts moving, it is governed by static friction, a force that actively opposes impending motion parallel to a surface. Watch the vectors on this block. Static friction is completely self-adjusting. As the applied pushing force increases, the static friction vector grows in the exact opposite direction, perfectly matching the push to keep the block entirely stationary. But it can only resist up to a strict mathematical limit. This equation shows that the maximum possible static friction is determined by the coefficient of static friction multiplied by the normal force. The moment your applied push exceeds that maximum threshold, the static grip breaks. The object suddenly jerks forward and begins to slide across the surface. Once the object is sliding, static friction disappears, replaced by kinetic friction. In this diagram, notice that the kinetic friction vector, F sub k, locks in as a constant force opposing the actual relative motion. Comparing the mathematical rules for both, experiments consistently show that the coefficient of kinetic friction is less than the maximum static friction. It takes less physical effort to keep an object sliding than it does to break it out of a dead stop. Friction operates as a dynamic transition that dictates the state of motion in a system. Finally, rounding out our primary toolkit, we have forces determined by displacement rather than surface contact or string tension. This is governed by Hooke's law. As the spring stretches outward, increasing the distance x, a restoring force F grows proportionally, pulling back in the opposite direction. These formulas for friction, tension, and springs are incredibly reliable. They allow engineers to solve nearly any macroscopic physics problem without ever needing to know the atomic details of the materials they are working with. But here is the strange truth underlying every calculation we've just discussed. None of the forces we just modeled, not friction, not tension, not normal reaction, are actual fundamental forces of nature. To see why, we have to look past the visible surface. Zooming in infinitely close to the contact point between the block and the floor, the smooth wood grain completely disappears, revealing a chaotic, jagged landscape of atomic structures. At this scale, objects never actually touch. As the atoms of the block approach the atoms of the floor, their negatively charged electron clouds repel each other with massive localized force. Every single contact force you experience, the upward push of a chair, tension in a stretched rubber band, the drag of a car tire, is just millions of these microscopic electrical repulsions added together. Trying to calculate millions of individual atomic repulsions just to find out if a wooden box will slide across a floor is mathematically impossible. So physics provides an empirical shortcut, packaging that atomic chaos into clean, usable formulas. The free body diagram is a necessary abstraction, a way to simplify the infinite chaos of the atomic world into a solvable human reality.